Good morning. Welcome back from the coffee break. My name is Zaidke. I was a bit late because of the bus connections here. It's my pleasure to opening the second session of this morning. And as you know, it's a Basque Quantum Technology and Information Workshop, but we are very happy that for many years now we have included our colleagues from Bordeaux in this event. And so we're happy to welcome Matthieu Saubanère from the University of Bordeaux here, and he will have the first invited talk, and he will speak about quantum subspace methods for electronic structure calculations. So please.
Perfect. Thank you very much. So it's a pleasure to be here. I really thank Enrique and Geza for organizing this meeting. And today I will speak about quantum subspace method for electronic structure. So, of course, today we can simulate property of matter at the quantum scale for very short time lapse or really small particle with different system, molecule, material, or even biological system, with very different kind of application from drug discovery, energy storage, conversion, quantum technology, and so on and so forth. And of course, we hope quantum computer will help us to address more complex system and more complex phenomena. The underlying challenge is, of course, to solve the Schrödinger equation, and which at the end is to diagonalize an Hamiltonian, so to find the eigenvalue of that matrix, and especially the low-lying energy level that contain the low energy physics information. The problem is that when you increase the size of the system, the size of the Hamiltonian is growing exponentially, so that it becomes untractable on classical computer. A numerical method that have been developed since decades to run on classical computer are, of course, exact diagonalization, such kind of Lanczos or QR method. But you find also a lot of approximation in order to reduce the pertinent active space to really a small one, or either wave function ansatz or perturbation theory. And finally, you find more or less the quantum analog to run on quantum computer, which are based on such paradigm. So typically, you have a physical problem. That is described within the Hamiltonian that you want to diagonalize. And I just draw a simple example of the H2 molecule that probably everybody know, where you have two orbital. I mean, the simplest vision of the H2 molecule is two 1s orbital that will interact, and that form either a bonding state or an anti-bonding state. And within a mean field approximation, so at the R3 Fock level, you will put two electrons on the binding states. So how you put that on a quantum computer? You just assign to one qubit, one spin orbital, so it's direct mapping, the Jordan and Wigner one. And so you can encode it with the up channel of the bonding, the down channel of the bonding, and the up and down channel of the anti-bonding orbital. And if you want to prepare the mean field wave function, the R3 Fock one, you just have to put an electron on each bonding orbital, and this is exactly this picture that is translated to initialize the states on a quantum computer. What you expect is to find a unitary operation such that at the end you get the exact ground states of the H2 molecule, taking into account electron-electron repulsion, so beyond the mean field approximation. So of course the game on the designing quantum algorithm for quantum chemistry or condensed matter physics will be to design this unitary operation that transform the initial states, in general the mean field solution, to the exact many-body ground states. So typically, what will be on this unitary transformation? You will have a number of gates to perform it, and of course, more you have gate, more it will be a problem with noise and quantum coherence. You have also the width. So we have seen that it's easy to encode one qubit in one orbital but you could find methods that enlarge the width, so increase the number of qubits such that to reduce the number of gates. And you have also a last parameter, which is the number of shots that you will have to measure in order to get the solution. So typically, there is a kind of an arbitrary separation between two types of methods that are believed to work on noisy quantum device, and methods that are designed for fault-tolerant quantum computer. So the NISQ algorithm, you require to have a really low depth, so really shallow algorithm, and you can allow to enlarge the size of the qubit, the size of the register, and also to have more shot. So typical method for NISQ computer are the class of algorithm which are variational, that are hybrid, classical, and quantum. So you perform a classical optimization such that you reduce the number of gates. Fault-tolerant algorithms are more based on quantum propagation. So the unitary transformation is more trivial in that case, since it's simply the exponential, the propagation. I forgot for the minus sign. You just use the propagation of the Hamiltonian. And recently, there is a kind of a hype on methods that are based on quantum subspace, and typically quantum Krylov method that also derive from the classical analog, which is the Krylov method or Lanczos method that I will describe now. So Krylov subspace method classically are the method of choice, and you have two ways to understand why it's work pretty well on classical computer. The first vision is more mathematical and arise from the power method. So you have an Hamiltonian, H, you renormalize it by the norm you want, typically the Frobenius norm, and here I represent it in his eigenvector decomposition, so only they have only entry on the diagonal of that matrix, and if you look the spectra, there is one element of that matrix which is dominant. So this is the value of each eigenvalue, and this one have been taken a bit higher than the other, just for sake of clarity. And so you start with H and an initial vector that is in general random, and you see that if you construct a new matrix which is just the power of the Hamiltonian renormalized, little by little, you will select the highest eigenvalue. So just by repeating, just by multiplying a matrix by itself, and by renormalizing it with this norm, within only few iterations, you find that HK is nearly a zero matrix with just an entry at the highest eigenvalue. So you have filtered the spectrum to select only the highest, the eigenvector with the highest amplitude, so that at iteration k, if you apply hk renormalized to the initial random vector, it gives you the ground states. So it's really efficient because you can see that the convergence is geometric. So it means that the error at each iteration is reduced systematically so that it breaks the exponential wall. It means this simple relation say that even you increase the size of the Hamiltonian exponentially, the number of iterations that you will need is only polynomial, so that it's something like look perfect. The problem in classical computer is that you cannot store, it's not a problem of algorithm efficiency, it's a problem of RAM or of memory. Because typically, to encode a vector V0 that have the number of coefficients which is the same that the size of a matrix, if you have, you take 16 orbital, the associate Hilbert space is 2 at the power 16, and so just to write on the RAM this V0, all the coefficients you need, it takes gigas and gigas, so that the problem is purely to a memory problem. What we call the Krylov subspace is finally only the ensemble of vectors that you create from V0 that contain the product for all k, hk times V0. You can see also the construction from a Krylov subspace with more a physical meaning. And you see that if you start with the propagation of an Hamiltonian on this arbitrary vector V0, and you make a Taylor decomposition of the exponential, you find naturally that at each time step arise power of the Hamiltonian. Okay? So that if you construct this Krylov subspace within V0 and H, you can diagonalize the Hamiltonian with a general eigenvalue problem because these elements do not have to be orthonormal. And you find really fastly the dominant eigenvalue. The difference between Krylov and Lanczos is just that within Lanczos, at each step, you orthonormalize the vector with the previous one. And you can show that for an Hermitian matrix, it gives you a tridiagonal representation, which is really easy to solve on a classical computer. So in this plot, I show you the convergence, so the relative error for a random matrix. You just take I think it's a 1,000 by 1,000 random matrix as a function of the number of Krylov iteration you do. So for the power method, when you do not orthonormalize the vector at each iteration, and for the Lanczos method with orthogonalization, and you see clearly that Lanczos outperform the power method, and the power method is typically what you expect as a kind of quantum annealing process. So that this parallel with a classical method and quantum method tell you that normally within a quantum Lanczos algorithm, you should either perform a quantum phase estimation algorithm so that it's perfectly suited for fault-tolerant computer, but also probably for NISQ. And with a quantum computer, you have no problem of memory issues, since to encode a vector V0 having an exponential number of coefficients, you just need a linear number of qubits. The main problem is that you know that I speak at the beginning that on a quantum computer you encode unitary matrix. The Hamiltonian have many properties, is Hermitian in particular, but is not unitary. So you cannot encode directly each operation that you need to construct the Krylov subspace on a quantum computer. So quantum Krylov method and quantum Lanczos in particular should outperform any method we have if we are able to encode this operation on a quantum computer. So typically what people have thought directly at the beginning is that the exponential of the Hamiltonian is a unitary operator. This is the propagation. So the simplest way to implement quantum Krylov method is to propagate starting from a V0 and to stop at each time step to recover power of the Hamiltonian, and so power h V0. So you have just to measure on a quantum computer the overlap matrix and the Hamiltonian, which is Vk, it's hk V0, and after you solve it you solve that eigenvalue problem on a classical computer. So it's fault tolerant because, as you see, at for each iteration, you will need to trotterize this operation on a quantum computer, and that will the circuit will become really, really long. I mean, if you typically for an electronic problem, the number of gate, the number of CNOT gate increase quartically with the size of the matrix to encode a single exponential EH tau being really small. So you will the size of the circuit will increase as the same. I mean, will become as the circuit will be as depth as with quantum phase estimation, especially because to measure this kind of non-diagonal element, you require an Hadamard test, which is also demanding in terms of gate. And also, because what you will measure becomes smaller and smaller, the number of shots is also increasing with the number of iterations. The alternative of this propagation is typically block encoding, if you heard about it. There is also many people that try you double the size of the system by an ancilla qubit, and on half of the Hilbert space you encode the Hamiltonian, and the rest is just made in order that the full operation is unitary. What we have worked on is to have a more NISQ approach to quantum Krylov, and to find a variational way to construct this Krylov subspace. And so for that, the main point is to find the cost function. In variational quantum algorithm, VQE, generally what you want to minimize is the energy, because physics is, thermodynamic laws say that the eigenvalue, the lowest eigenvalue will have the lowest energy, so you have just to apply the variational principle and to minimize the energy, and normally if the minimization process goes well, you end up with the ground states. What we have shown is that if you switch the cost function, but now you will not minimize the energy, but you will minimize the first non-diagonal element, the square of the first non-diagonal element. This is equivalent to 0, the column and the line given the initial vector. So you start with a V0 there, and you want to find another state phi1 such that the overlap or the interaction within this variational states is maximal. And if you go to iteration 2, of course, you will minimize you will maximize or minimize minus the square of that element, and so on and so forth. And at the end, you are supposed to get a tridiagonal form of your Hamiltonian. And since tridiagonal representation of a matrix is unique given given a vector V0, it's strictly equivalent that to build the Lanczos, that to run the Lanczos algorithm. So this cost function allow us to say that we will use it within a variational approach, and the tridiagonal form that we obtain at the end should be strictly equivalent that the one we should have within Lanczos algorithm. So if you want a more physical picture, you start with your initial state phi0. This is the variational state that you want to construct on the quantum computer that depend on variational parameter, and you will determine this variational parameter such that to maximize this interaction there, and so on and so forth. And at the end, normally after a number of iterations, you should get the ground state energy and the ground state vector. So we have tested that on real with the most basic test that we could find. We take the linear H4 molecule, so nothing yet really exciting from the point of view of physics, and we have taken the most simple variational circuit that is available, which have been proposed now nearly 10 years ago by people from IBM, which just consists of a layer of RY gate within after linear entangling gates. And you can you can build this variational circuit with an arbitrary number of layers, so you have well control of the circuit depth as a function of the number of the layer. And so this is the results that we obtain within this framework. So at each time we try to minimize or maximize the interaction energy between our first vector, our initial vector and the variational one. And this is just the energy respect to the classical value we should obtain, since we have a really short circuit. We not expect to span the entire Hilbert space efficiently to get exactly zero. But however, we see that as a function of the number of layers, it's increase. It's the error. I mean the difference between the optimal value and the error we got with our variational algorithm decay with the number of layers. And this is typically the problem of variational. The variational problem is that the potential energy surface is highly non-convex and without too many Barents plateaux, so that if you start with different initial variational parameter, you do not all the time get to the minimum value. However, we could show that this cost function show much less problem than minimizing the energy, because you can, I mean, typically the problem is not in the convexity of the energy as a function of the unitary, but more the non-convexity of representing a unitary transformation by a quantum circuit. So you have many quantum circuits that can represent the same unitary transformation, and that make the optimization issue. However, they are much less than with a traditional variational quantum eigensolver. And so in this plot, we are still with only one. We are now with only one layer hardware efficient ansatz. So 8 C0 normally before the Hadamard test. It will after the Hadamard test, you will have about between 30 to 50 C0 depending the way you do it. And in 30 C0 within only 16 variational parameter. And on that plot, I represent the energy as a function of the bond length. So what is called so typically you have the exact solution in black under the line, and here you have this energy as a function of the bond length for different number of iterations. So this is the starting vector, so the Hartree-Fock approximation, and already with one iteration you get better, with 2 iterations you get better, and you fastly converge with less than 10 iterations to the ground states. And here is the error on the error plotted as a function of the bond length. And you see that typically you pass the threshold of what is called the chemical accuracy. So what we would like to the precision that we would like to have a pertinent post-processing. And you see that with already 5 to 10 iteration, whatever is the bond length, you get a really good estimation of the ground state energy. This curve is maybe the most important one, because this is the error as a function of the iteration. And what you expect for geometric convergence, so to break the exponential wall, is within a logarithmic scale on the error, you have a linear behavior, which means that at each iteration, the error is divided. And these lines are the classical Langsos algorithm. The gray is exactly the Langsos algorithm, but when you do it with a variational approach on a classic computer. And in color are the results when you use an hardware efficient ansatz. Okay? So of course, if you use an hardware efficient ansatz and you do not perform exactly your variational problem, you do not recover exactly what you get with the classical algorithm. However, you have this linear dependence on the error with the number of iterations, which means that you have a geometric convergences and that the job is done somehow. At some point, you might have a plateau. This kind of plateau that have no link with Barents plateau or stuff like that, this is, you have it also with classical Langsos, and it becomes you have quasi-degenerated states. And there is a famous theorem for the classical Lanczos algorithm, which is the Caniel-Page theorem, that more or less say that the error will decay as the first excited gap over the spectral width at the power of k. And so if you are degenerated or quasi-degenerated, it means typically that the gap between the ground state and the first excited state is really low, is really slow, and so Lanczos algorithm, even classically, perform much less. But you see that even if with less than 10 iteration, I mean with only few iteration in that case, you already got the objective of the chemical accuracy. Finally, that is the same, but for the states fidelity, which you see again this kind of you find that the fidelity is also really decreased. I mean, the fidelity is improved by the number of iteration, whatever is the bond length, and this typically compared to the expected fidelity for the power method that depend on the gap, the ratio between the first excited gap and the ground states. So at large distance, you have quasi-degenerated states. The reason why the algorithm perform a bit slower, but you got fidelity with a number of iterations. That the number of iterations will increase finally a bit more that at the low distance when the gap is large, but you will still at the end the numerical effort will be a bit higher, but you will get something that converge in a polynomial way anyway. This is just the results for the charge gap. The charge gap is something which is far non-trivial to compute, and that depend on the ground states and on excited states, so that it's a bit difficult to get. And you see again the R3 is pretty bad over the especially at high distance, but within only 5 to 10 iterations with the Lanczos algorithm, you recover perfect estimation of the excited gap. So that was just to mention you that quantum Krylov method are kind of or quantum subspace method in general is a nice framework for the transition from noisy computer to fault-tolerant computer. It benefits from the fact that it converges really fastly on classical algorithm. The only point is to be able to construct the Krylov subspace on a quantum computer, which is less trivial than on classical computer. And within variational approach is supposed to be more resilient to sampling noise and optimization issue. Just a short advertising on the second Basque Country Bordeaux workshop on quantum algorithm that we organized with Yacine and Javier. Last year was quite a good success, and so we will do it again with the same format than last year, the 24 and 25 March, again in Bayonne, and we will soon communicate more about it. The scope of the meeting will be against quantum algorithm for physical and chemical application, for optimization and quantum Monte Carlo method, quantum cryptography, error correcting code, coupling with HPC and more. And so that the people that were involved in this work in Bordeaux, and Bruno, collaborator in the Charles Garret Institute in Montpellier, and I thank all of you for your attention.
Thank you very much, Matthieu, for the nice talk. The floor is open for questions.
Hi, thanks for the talk. How do you compute the excited energies variationally on the last slide or previous to last?
So typically you see that is not depend on you have not the same number of electrons.
Okay.
So typically, if you start, I mean, if your if your ansatz is symmetry preserving, the question is known. But in this case, you start with different initial state with different number of vector. However, I mean, I just show results for the ground states, but the first in a low energy, the low lying energy states are whatever already reproduce within the symmetry subspace. So because you construct the Krylov subspace, you have access not only to the ground state, but the low lying states. You have the Caniel-Page theorem that is the convergence on the ground states, but the first excited state converge also really fastly. But in the same subspace, the same symmetry subspace that the original one, normally.
Okay, thank you.
Hi. Yes, I had a question, maybe it's naive, but on the beginning you mentioned this in the power method that the error, the error between lambda 1 and lambda 2 is higher with the k, but does it depend also on the dimension of the Hamiltonian or not?
Actually, so the number of iterations that you will need depend on the size of the Hamiltonian somehow, but you see that and on an initial state also. I mean, the Caniel-Page theorem, more or less the heuristic version of the Caniel-Page theorem, say that the error converge of 1 over the overlap, and after, at the power of k, the ratio between the first gap between the spectral width. So if you start with a vector which have already a large overlap, you will have a small number of iterations. But whatever, if you start with a random vector which have a really low overlap, the second part of the error as a function of iteration will fastly take the asymptotic limit, and so you converge in a polynomial time, whatever is the size of the system. I mean, you increase exponentially the size of the system, the number of iterations to get the same accuracy increase only polynomially.
Okay, thanks.
Thank you very much. I think we need to move on to the next talk, so let's thank Matthieu again.